So this lecture is over the fundamental theorem of the calculus. It is the crowning glory of the course. Before we get to it proper, we're going to touch one or two other things. We're going to define something called a Riemann sum on this, which is kind of a slightly different approach than what we've had with our upper sums and lower sums. Let f from the closed interval ab into r be a bounded function. Let p be a partition as usual. And suppose that t is an ordered set of real numbers where ti is an element of the interval xi minus 1 xi for I equal 1 to n. Then t is called a selection for p. All right, now let us now define r sub p of f comma t to be the sum from I equals 1 to n of f of t times delta xi. We say that r sub p of f comma t is the Riemann sum of f with respect to p and t. Note that the Riemann sum is always between the lower sum and the upper sum. All right, now we can take a limit on our Riemann sum on the partition in the following way. Suppose that for every epsilon greater than 0, there is a partition Q of the closed interval AB such that Rp of ft minus I in absolute values is less than epsilon for all t whenever p is a refinement of q. We say that I is the limit of Rp of ft, and we write it as lim p Rp of ft is equal to 1. All right, so we'll now use this new definition to give us a new characterization of the Riemann integral. So let f from the closed interval ab into r be a bounded function. Then f is Riemann integrable on ab if and only if the limit of p of Rp of ft exists and is equal to a single value I, regardless of the choice of t. And in this case, that single value I is equal to the integral. Okay, this is an if and only if, and so our proof will begin by supposing that f is Riemann integrable. We'll then show that the limit exists. Okay, so let I be the value of the Riemann integral. Let epsilon greater than 0 be given. Then there is a partition Q of AB such that U sub Q of F minus L sub Q of F is less than epsilon. All right. Now, let P, as usual, be a partition of AB. Since the Riemann sum of RPFT is between the lower sum and the upper sum, and the integral, or the value of the integral I is between the upper sum and the lower sum, then the distance between the Riemann sum and the value of the integral is less than the distance between the upper sum and the lower sum. Now suppose that P is a refinement of Q such that such that the distance between the upper sum and lower sum is less than epsilon, it will then follow that the distance between RP, FT, and the integral is less than epsilon. Therefore, our limit exists and is equal to I. And notice that this choice is completely independent of our choice of t. All right, now let's go the other direction. Let's assume that this limit exists regardless of the selection of t. We'll first show that u of f equals I, and then that L of f equals I. To show that the upper Riemann integral of f is equal to I, let epsilon greater than 0 be given. Suppose that P, as usual, is a partition of AB. Now for every I equal to 1, 2, 3, 4, up to n, let T sub I be in the ith subinterval, be chosen so that m minus f of ti is less than epsilon over b minus a. Then we can, just by a simple calculation, see that u sub p minus r sub p of ft is less than epsilon. And it follows smoothly along in the calculation. You should have no trouble discerning the reasons for the steps at each stage. So u sub f is within epsilon of I. Since u sub f and I are fixed and epsilon is arbitrary, it follows that u sub f is equal to I. By a parallel argument, we can show that LF is equal to I. Therefore, it's Riemann integrable, and everything is what it should be. Now, we come to the fundamental theorem of the calculus. Suppose that f from the closed interval AB to R is continuous, and that f prime of x is equal to little f of x for every x in the interior of the interval AB. If f is Riemann integrable, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. Okay. We start our proof having it with a partition p equal to what we usually have it equal to. And then here we take a zig. It's kind of fun. Consider f of b minus f of a. Then the sum from I equals 1 to n of f of x minus f of x I minus 1 is equal to that. It's a telescoping thing that's going on. Okay. By the mean value theorem, there is a ti in the interior xi minus 1 xi such that the difference between f of x I and f of xi minus 1 is equal to f of t times xi minus 1. We can therefore roll this into the previous expression, and we have that f of b minus f of a is equal to I, the sum of I equals 1 to n of f of t xi minus times xi minus xi minus 1, which is just equal to the sum of I equals 1 to n of f of t I delta xi, and this is equal to rp of ft, our Riemann sum for this particular selection. All right, so since f is Riemann integrable, that limit exists, okay, and is the same thing for every selection of t. And since for this particular, and it's equal to the integral from a to b of f of x. Since for this particular selection of t, this limit is equal to f of b minus f of a, we get that our integral from a to b of f of x is equal to f of b minus f of a. And there's our crown jewel.